Okay, let's try this one now. So if the square of one side of a triangle is the sum of the squares on the other two sides, then the angle opposite the first side is a right angle. Okay, so you're given a triangle A, B, C, and the square of one side, so we'll just say you're also given the fact that AB squared equals BC squared plus AC squared. Then we're required to prove that this angle here, the angle ACB, is 90 degrees. Okay, so the proof here is to draw AD perpendicular to BC. So just draw a line here that makes it perpendicular, and we'll call that D here. So what we can say is that AB squared equals AD squared plus BD squared from Pythagoras, and also from Pythagoras we can say AC squared is AD squared plus CD squared, like that. So okay, now what's the next move? Okay, so if I subtract these, they would cancel, and I would get AB squared minus AC squared equals BD squared minus CD squared. But just remember what AB squared is. So if I put that in here, I'll get BC squared plus AC squared minus AC squared equals BD squared minus CD squared. So they cancel. And I get BC squared equals BD squared plus DC squared, or I should say, CD squared. So BC squared equals BD squared plus CD squared. Isn't that right? BC squared, that length there, squared, equals this length here squared plus this length here squared. Now, that's not possible unless CD is 0. So, I mean, I'm not sure what the theorem is called, but if you have a length here, let's say that's just length A, and that's length B, okay, for example, or I should use different letters here just to not mix them up. So if we call that X here, and that's Y, and that's Z, X equals Y plus Z, but X squared does not equal Y squared plus Z squared. So I think what I'll do to finish this off is just to say, note that BC's length equals BD's length plus CD length, and that means that BC squared cannot equal BD squared plus CD squared, unless, and the only way that this could be true, so that we don't contradict earlier, unless the length DC, this length here, this D and C coincide, unless CD equals 0, i.e. D equals C, i.e. That this D and C line up because C is 90 degrees. Angle C is 90 degrees. QED. Okay. That proof is a tiny bit different to what's in the book. Just because I really don't like the move that they made in the book at the start, where they said, draw a line AD that's perpendicular and bisects it. And I just feel like you can't really say both. That's too big of a move in one go. You could draw a line that's perpendicular, or you could draw a line that bisects the BC into two equal parts. But I don't really think it's right to say you can do both at the same time, because there's no guarantee that you can do that. It's not. I don't think it's a legitimate first move. That's what I think. It makes the proof a tiny bit shorter, but not much, and I don't think it's a fair move to make at the start.